All right, let's get started. Hello, everyone. Here's Zhiqi. So I'm about to present my final project. So it is about chemical lab simulation specific to gas diffusion. So simple introduction of my project. So this applied project, I'm about to create a program or independent application to fully represent the process of different modules belongs to gas diffusion fields. So the project itself is a simulation. That's the first keywords. Uh, so I'm going to visually display the process of gas diffusion. Uh, Plus, it will do data collection and calculation. So overall, the goal of this project is to, well, first of all, show gas diffusion phenomena to the users. It could be a experiment tool to chemical engineer or a education tool for the chemical staff learner. So the utilities I'm using, the primary one is GreenFood. It is a free open source game engine developed to address Java code and also some embedded functionalities for UI, visually UI. So that's why I choose this tool based on my personal skills. So I'm kind of using Java language to do the main programming thing. And partially I pretend we'll use Python to deal with some graphical data and some data collection. So to explain my project, I will start from the flow diagram, or the use case diagram. So the customer, or I should say user, firstly, they will need go through the login page, and the login page is controlled with a access admin control, and once they use two-factor authentication, which is the basic authentication, the username and password to pass through the login. And then they will go to the module selection page. They would the user would be routing to the subfields, the subpage, which is the main content of the project actually. So it is divided into three modules. The first one is gas kinetic movement, and then gas diffusion, and then gas effusion. And when the user finish observing or uh, letting the program run to generate data, it will meet the final state. Then it will run a result report to calculate data, to collect data, calculate data, and then restore the result into the file system. Well, initially I would like to do in database, but I'm assuming that's too big. So I would just do like in the file system storage. So the module one, gas kinetic movement, it's based on the ideal gas law. Each particle represents a gas molecules. So they moving randomly, sort of randomly, based on the behavior of Browning's movement. Uh, D here, the capital D represents the diffusion coefficient. So it is calculated based on those parameters. Some parameters are preset in the program. Some data are provided by user. And also by selection, the drop-down list, the checkbox, or the vertical bar, uh, horizontal bar, I mean. So the user could address or loading those gas particles and see how it moves, and finally see the data being calculated about kinetic energy, diffusion coefficient, and some other data results. So to help user understand how gas diffusion works, how gas kinetic movement works. The module two is gas diffusion, also called multi-phase diffusion. So let's see, here is the container, and in between there is a green line, which is a semi-permeable film. So this film would allow different types of gas particles to move through, like the green balls could move to the right side, and of course for the opposite way. Uh, but the semi-permeable film will slow down the movement of gas. Here, it, the calculation is depends on fixed first law. So still, J represents a different type of diffusion coefficient. Here, C represents the concentration. So the concentration difference will be the main force to driving the gas particles move through this film. And once the concentration is equal for both sides, then the process reached to the end state, and then data calculated and the result generated, things like that. So so here the concentration is the key. And module 3 is gas effusion, also called pinhole effusion. So in this module, the key is actually the pressures. So uh, one side we will load massive of gas, and here is a wall. Typically, the gas would not allowed to pass through this wall, but notice here we left a small hole there, so that's a pinhole, and the gas will move through the pinhole to the other side. Uh, Differences to module 2 is uh, the main force is derived from pressure. So let's say if on the left hand side the pressure is lower than right hand side, then when the gas move out through the pinhole, it will be accelerated. But if the pressure on the left hand side is higher than right hand side, then when the gas particle moves out through the pinhole, it will be slowed down. And if here is a wind that's potentially air flow happens, it will also accelerate the gas movement because, as we know, the pressure will be lower when air flows. So here we are going to do the effusion rate based on this equation. Uh, all the controls uh, should, all the three modules, the control should follow the real natural system uh, based on the gas diffusion laws, the principles, and the speed uh, and other properties or like effusion rate, diffusion rate. Those things are calculated from equations, formulas uh, derived from parameters either previous site, predefined, or provided by user. So after the user see all these behaviors, they should also viewing a another separate independent diagram, which sort of controlled by Python. So they will see vertical bars, result being calculated, or this chart to see the lines and curve, the result they see. Well, here, to be honest, this is a sample. This is not. This is a real sample. This is not. This is just a half-finished Python code to generate my result report, data report, things like that. Overall, that's all my project. Thank you for listening. Have a good time. Bye.